one. So there's many things that we will be able to do with calculus that we were not able to do without calculus. And let me give you some examples. So number one, evaluate a function, for example. What's going on here? Okay, perfect. Evaluate a function. Okay, it only gets up to here. So we have x and f of x. Okay, what did we do in algebra? Well, plugging a value of x to a given function of x to basically get what we usually call the height of the function, you know. But with calculus, so that's with. Okay, let me move this. Come on. Okay, I got everything. All right. So without calculus versus with. Okay, I see the limitation here. Got it. So with calculus, we'll see instead the value x approaches, the value of y that x approaches to when we are approaching certain value of x, and that's going to give rise to the concept of limit in this case. Well, another piece of information, well, that we did without calculus, well, finding the slope of a line, which is the delta x and the delta y, m equals y2 minus y1 over x2 minus x1. But with calculus, we will be able to find the slope of a curvy shape in this case. All right, back in algebra, we were able to find the slope of only linear function. Well, in terms of the equation, that's the value that multiply the x's on the variable for the equation. And in terms of how we find the slope, is the ratio of the rise to the run. But that was limited again to only linear equation or linear shapes. Now we're going to do do the same, or we're going to extend the idea and the concept to find the steepness at a point right here. The steepness at a point which actually, in comparison with the line always has the same steepness, the same slope, but in this case, a curvy shape has different steepnesses at different points. So that's what we're going to do with calculus. Well, average velocity without calculus, well, so we have a particle in motion, a particle, well, it could be a car, it could be an airplane, or someone walking between t equals a to t equals to b. Okay, so in this case, well, we're going to find the average velocity using algebra. However, using calculus, we will be able to find the instantaneous velocity at a particular point. For example, well, so you travel from San Diego to Los Angeles, well, it takes 120 minutes, roughly 2 hours, and it's, let's say, 120 miles, right? Well, 120, well, no, maybe, well, it takes 2 hours, okay? Let's say it takes usually 2 hours, but I mean, your average speed that you drive is 60 miles per hour if you do some calculation. However, that's not always the case, because there's portions of your trajectory in which you go faster. Sometimes you speed up to overcome a car, or you run into traffic, you have to slow down. So in reality, that speed, it's not always the same, it's not uniform. So in that situation, we are going to use calculus to find that velocity at particular time, not just the average velocity, which is initial point and terminal point, which is the time it takes to go from point A to B. Another thing we're going to do, well, I already talked about the height of the function. Let me talk about that again. f of x, which represents the height of a function. However, with calculus, we are going to learn tools to find not just any height. For example, we would be interested in finding the maximum value of a function, or the maximum height. Because, well, what happens with algebra? Well, you could do it with algebra and make a table. For different values of x, you will be getting different values of y, and then you're going to see increasing values of x, then reach a maximum, and then you will see decreasing values of y. But that's not the most practical way to determine the maximum of a function. It's too exhausting to just plugging in values. So we're going to learn tools in this class to find those maximum and minimum values. Well, if you have taken calculus classes in high school or something, well, maybe you have an idea of what are we talking about here. But if you haven't ever seen this, well, this is the class where you will learn how to do that. Well, what else? So let's move on to other applications that we do, like area. So we can very easily find the area of a rectangle, length times width, right? That's how we find the area. However, what about the area of a weird shape like this? Alright? Well, there is a problem with finding areas like this. Well, so we have tools like a ruler to measure the length, measure the width, multiply the numbers, that's the area. But over here, do we have curvy rulers to measure this length exactly? Not really. Well, you may have seen some curvy rulers for designers and the like, but I mean, every curve has its different shapes, so we cannot build a ruler for every single shape. So in this case, we're going to use calculus to find areas of weird looking shapes like this, or even something weird like this, you know, an area like this. And that's the end of Calc 1 and mostly covered in Calculus 2. What else are we going to do with calculus? Well, so in basic science, in basic physics, for example, the work done by a constant force, right? But in this case, but in reality, in practice, when the work done by pushing the table, for example, or let me just push the table really quick, I'm not exerting a constant force, and actually I'm not exerting the force perfectly horizontally. I'm actually with an angle. So this idea of working with force, number one, that force will be variable, right? It's not going to be the same all the time, and it will also be variable and also with some angle theta. This is Calc 2 and Calc 3 material. So in Calc 2, well, we're going to look at how to find the work of a variable force, and in Calc 3 we're going to include, or rather to incorporate the concept of vectors, the idea of vectors and multivariable functions to find the work done by variable force in different ways to define this function. Okay, so that's pretty much the motivation to study calculus, because calculus will be a very powerful tool to solve these problems that otherwise we would not have been able to do just using algebra, plugging in just values. So we need fancier tools in this case, and in particular, well, that's calculus. But well, the tangent and the velocity problem. So let's, number one, talk about instantaneous velocity versus average velocity and all that. And well, so from here we are going to construct other ideas that we will put together to limit, and then later to other very important concepts that I don't want to spoil the whole plot of the movie here. Alright, so what about the tangent problem? Well, so consider the following graph. Oops. No, I don't want that. I want this. Okay, so we can consider this graph of some function, any random function. And well, in this case, there's a couple of things that we can do. Number one, let's trace a secant line. Recall that a secant line is a line that crosses a function, or crosses a graph at 2 points, right? And well, so we have tools to find the slope of a secant line. And well, in this case, this is the point x2, y2. This is the initial point, or q rather, and this is the point 1. Okay, let me call this p2 instead. x1, y1. No, it's too messy. So p2, that's a q, p1, x1, y1. Okay, so we have tools to find the slope defined by these 2 points. We already talked about it, didn't we? Isn't that the slope m equals y2 minus y1 over x2 minus x1? Alright. However, the case that will give rise to the whole calculus here is the problem of the tangent line. Well, how do we find the slope of a tangent line in this case? Come on. Well, slope of the tangent m, well, that we don't know. That's what we're gonna do today. How do we find the slope of the tangent? Well, and in this case, let's start with a very basic example using the idea of finding the velocity. Well, so let's do the basic case for the average velocity. So you take a trip in your car and you notice that after 3 hours you have traveled 180 miles. What's your average velocity? Well, this is a basic distance over time problem, you know. So in this case, well, let's label V average. That's the change in position over the change in time. I know it's just distance over time, but again, calculus, you can think of calculus as the mathematics of change. And in this case, well, we're going to talk about this in terms of change. So when we discuss what a derivative is, a derivative is the change of one variable with respect to the change of another variable. Well, let's not get too ahead right now. Let's keep this simple. So the change in the position, which is 180 miles, over the change in time, which is 3 hours. That is 60 miles per hour. Well, which is a decent answer, right? It makes sense with the context, right? Not driving at 60 miles per hour, why not? Alright, so we're going to make this problem a little fancier under a different situation. Yes?
That's supposed to say change position.
Yes, that's supposed to be change in time. Yeah, thank you. Change in time. Alright? Okay, so let's take this idea of velocity equals distance over time into what we call the average rate of change. And we already did a picture of what the average rate of change is. Let's go back to the other slide right here. So in which we discussed how we find the average velocity by finding basically the slope between the 2 points. So let's see. So the average rate of change of a function is, and that's something you may have done also in algebra, intermediate algebra, pre-calculus. And well, we're going to incorporate this idea of the average rate of change into the velocity problem. Well, because this basically looks like y of b minus y of a over b minus a. This looks like the slope, isn't it? y2 minus y1 over x2 minus x1, but in this case we're coming up with different labels here. Alright, so this is the average rate of change. Now I'm going to label this AVH. Alright, well, so let's put a problem into context. So let's see, let's find the average and instantaneous velocity for a situation right here. So what do we have? We have a ball that is dropping from a tall building. The position S of t measured in meters after t seconds is given by this equation right here. S of t equals 49 t squared. Okay, 4.9 t squared. All right. What is the average velocity of the ball over the time 2,5? Well, you might want to label this as the A and this as the B. That's the initial point and the final point, or rather the initial time and the final time. So we're trying to find the average velocity. So let's draw a picture. How about draw a picture? And then the ball is dropped down. Okay. And well, we want to find out what's the average velocity at t equals to 2, between t equals to 2 and t equals to 5. Okay. So we're going to use the formula above, that is y average, or rather v average, not y, it's v average, that's the average velocity. That's s evaluated at 5 minus s evaluated at 2 over 5 minus 2. That is, on the equation, on the function that we have here that describes the motion of this ball that is dropped from the tall building, whenever we see the letter t, we're going to replace with a 5 and replace with a 2. That is 4.9 times 5 squared minus 4.9 times 2 squared over 5 minus 2, which is 3. Well, after doing these calculations, we should get the following result, and you can verify this using a calculator. We should get 34.3 meters per second. But again, in the context of physics, again, this is only an average velocity, because what happens? Due to the acceleration to the center of the planet, when you drop an object, the velocity increases as it goes down. So at t equals 2, well, it's going to go at a slower velocity than it goes after 5 seconds, and that's due to gravity. And considering the mass of the object, well, in this case, we are neglecting all those properties, or maybe they're just included in the formula. So we're only relating position versus time. So we don't want to turn this into a multivariate problem. So well, that's one example on how do we find the average velocity between 2 seconds and 5 seconds. Okay, so for part 2 of the problem, find the velocity of the ball after 5 seconds. There's an issue here, because how do we find the velocity after 5 seconds? We don't have a function to find velocity. The function that we're given is to find the position. Well, so this is what we're going to do in this case. So, number 1, how can we get instantaneous velocity based on average velocity? So one way is to say, let me keep going over, let me zoom it in here so you can see what's going on. Okay, so if I keep going to t equals to 6, do you see that this interval of time between 5 and 6 is smaller than the interval from 2 to 5? So this is 3 units far, and this is only 1 unit far. Alright? Okay, so in this case, I'm going to find the average velocity between 5 and 6, and let's see what we get. So for a moment, we're going to do a few calculations. Let me call this V average. and in this case between 5 and 6. Okay, so that's going to be S evaluated at 6 minus S evaluated at 5 over 6 minus 5. That is 4.9 times 6 squared minus 4.9 times 5 squared divided by 1, because 6 minus 5 is 1. Well, what about the quantity? So if the result for this should be 53.9 meters per second. Okay, so in this case, I'm making this interval or the average smaller than the interval between 2 and 5, which is a larger scale interval. So what I'm going to do, I'm going to keep making this smaller and smaller every time. All right. So let me zoom it in again. What if in this case, check this out, instead of considering the interval from t equals to 5 to t equals to 6, which is, I mean, it's only 1 second difference, but it's a big difference. However, if I go from t equals to 5 to t equals to 5.1, isn't that a way smaller interval? Isn't that like getting closer to the actual instantaneous velocity to 5? Okay, let's compute that. Let's compute that. So V average between 5 and 5.1. When we compute this quantity, that's S of 5.1 minus S of 5 over 5.1 minus 5. That means, well, in the denominator 0.1, and we're going to have 4.9 times 5.1 squared minus 4.9 times 5 squared. In the numerator, we should get the following quantity, 4.949 over 0.1. If we divide these two numbers, we should get 49.49. All right? Okay, let's list those over here. So that's the time interval 5 to 5.1. All right? Okay, but we can do this even smaller. We can get closer and closer. How much closer? Well, let me zoom this in again. How about we get even closer? Maybe not 5.1. How about even closer to t equals 5.05? Aren't we getting closer to the instantaneous velocity at exactly 5? Well, in this case, well, I'm not going to do the calculation, or actually, no, never mind. No, I'm not going to do the calculation. Okay, so that's 49.49, and then between 5, I will just give you the results. I have them here. But what I want you to see is the picture here. 5.05. If we did the calculation, we should get 49.049. But can we get closer to that value? Of course, we can do that. Instead of having to get to 5.05, we can go to 5.01, which is almost touching the 5 itself, or even 5.001, which is practically 0.5, which is actually 5. See what I'm saying here? See where we're going to? So by finding average values between differences that are really, really tiny, we will be able to see a trend in the values and predict what is the instantaneous velocity. Well, let's fill in the table with the calculations here. So what if I did between 5 and between 5 and 5.01? What about between 5 and 5.001? All right, so if we did this calculation, 49.049, and 49.0049. All right. Well, maybe if we do from 5 to 5.0001, this would be 49.00049. Okay, looking at these values right here, let's answer the last question. If we were to guess what instantaneous velocity when t equals 0, what are those average velocities getting to as we approach to 5? What would be the best number, the best guess? Yes. 49. All right. 49 meters per second. Okay. However, well, this is just a picture of how we get or how we would have done it without calculus, rather with the techniques that we know from algebra, because well, here we're not doing any calculus yet. We're doing what we know from algebra, take advantage of those tools to, in a way, not actually getting the exact answer, but we are predicting values based on observation for different intervals and having smaller intervals every time. But of course, that's not how we're going to do it. Let's do another example. Okay, let's do another example. Find the average rate of change for the function x squared plus 2. So now let's put the velocity on the side and let's focus on a natural function f of x, on an algebraic version of it. Okay, so again, AVH, which is the average rate of change, that's f of b minus f of a over b minus a. All right. So, number one, let's find the average rate of change between 1 and 2. So that is AVG rather, average between, not t, in this case it's actually x being between 1 and 2. This will be f of 2 minus f of 1 over 2 minus 1, where f of 2 will be obtained from 2 squared plus 2, plugging in the function, that's the 2 squared plus 2, minus 1 squared plus 2, divided by 2 minus 1, which is just 1. Simplifying this, what do we have? 2 squared, which is 4, plus 2, that's a 6, minus 1 squared, which is 1, plus 2, which is 3. Over 1, that's just 6 minus 3, and that equals to 3. So that's one calculation. Let's see what happens on the second interval. The average, of course, we're not going to compute all of them. I'll show you one way to get this done. Between 1 and 1.5. That is f of 1.5 minus f of 1 divided by 1.5 minus 1. Well, so what are we going to do? Evaluate the given function f of x equals x squared at the values of 1.5 and 1. That is 1.5 squared plus 2 minus 1 squared plus 2. So, and then divided by 1.5 minus 1, that's a 0.5. Okay. So 1.5 squared plus 2, that should give us 4.25 minus 3 over 0.5, and simplifying this should give us a 2.5. And then, well, we will see what values are we going to approach to. However, well, I'm going to show you a different way. So instead of just doing all these calculations, f of b minus f of a over b minus a, let's find a formula in general. Okay, in general. So in general, the average, at least for this function, not for every single function, the average between x, a, and b, it will be f of b minus f of a Same formula over b minus a. Well, applying this to the function that we have, which is x squared plus 2. So what we're going to plug in x squared plus 2 at b and subtract whatever we get from plugging in at a. That is b squared plus 2 minus b squared, a squared plus 2. Right? And divide that by b minus a. Well, what are we going to get from here? Number one, let's distribute the negative to get, okay, b squared minus a squared, and 2 minus 2, the 2's cancel here, and in the numerator we only get this b squared over a minus a squared over b minus a. And we can simplify this expression using algebra, because here in the numerator we have a difference of squares, which can be factored as b minus a times b plus a, and divide this by b minus a. And we can see here we can cancel out the b minus a's, and the average rate of change between x equals to a and b is simply b plus a. So instead of doing all these calculations as to f of b minus f of a over b minus a, all we can do is add b plus a. Okay, let's see if it works. What is 1 plus 2? Because this is a and this is b. Do we agree? So 1 plus 2 equals to 3. Isn't it the same as we did with the long calculation? What is 1 plus 1.5? 2.5. Isn't it the same as that we got here in the second calculation the long way? Okay, without doing this f between 1 and 1.1, instead of doing this 1.1 squared plus 2 minus 1 plus 1 squared plus 2, we can just add 1 plus 1.1. What is that? 2.1. What about here? 2.01. And if so, what are we doing here? We're getting an intervals that get smaller and smaller and smaller every time, aren't we? By doing that, we're getting from average to instantaneous. So now, let's take a guess. Take a guess. Instantaneous rate of change will be what would that be? So notice we're going from 3, 2.5, 2.1, 2.01. If we make this every time smaller, 2. So m equals to 2. So that's the slope of the tangent. Alright, that's the slope of the tangent in this case. Alright, so let's put this on a graph. So what do we have here? So let's go to the next page. And we have the graph. Okay, this graph that is this curve in black here is the graph of f of x, or y equals x squared plus 2, which is a parabola shifted up 2 units. And well, what do we have? Is this parabola right here at 2 units up, and it continues its counterpart on the left hand side of the y-axis. Well, so this is what we did in what we can do, but in this case, instead of going from 2 to any other point, we're going to look at the interval from 0 to 1. So what's going to happen here? So we have the secant line. All these are secant lines between these intervals, and notice the blue line right here, it's crossing 2 points on on the parabola. And well, on the next line will be the green line. The green line is using instead of going from 0 to 1, from 0.5 to 1, that is that slope. These 2 points right here are getting closer as opposed to the blue one. Well, from the orange line will be the slope between 0.9, which is kind of hard to see, and last but not least 0.99, and that's how we get close from average rate of change or average slope to instantaneous rate of change, instantaneous slope. All right, and if we look at this average rate of changes here, okay, we're going from 1, 1.5, 1.9, 1.999. All right, so these are secant lines. No, not all of them. Secant lines. And well, it looks like the red one, it's very close to be the tangent line. All right, or approaching to a tangent line. So that's how we go from secant line to tangent line, by observing these intervals and making them smaller and smaller every time. So it's important to see the difference between the two. So in a way of a summary here, the average rate of change, it's only an estimate. Again, that doesn't give us the actual value. It only gives us the average between 2 points. So in this case, for the average rate of change, we need 2 points or 2 inputs. For the instantaneous rate of change, we only require 1 input, or only, so basically 1 piece of information. Secant, 1 input, and that's the tangent. All right. Well, so now that we have in a way found the best guess, okay, best guess, for the slope of f of x equals x squared plus 2 at x equals to 1, what would be the best guess of the slope? So we go from 1 to 1.5, 1.9, 1.99. Most likely, if the pattern continues, it would go to 1.999, 1.99999, etc. What would be eventually the value? M equals to 2. All right. So yes, this is like the rough way to calculate the slope, but I mean, this is only the motivation, hopefully not a demotivation, because looks weird, looks like lengthy and crazy. Ultimately, we're going to do this in a few steps when we get into the limits, derivatives, into the derivatives and all that. We're not even going to do this, but this is only to see where or how we are constructing all these ideas of limits and later the derivatives. Well, now, so the next one, the last page, it's a very classical problem that we will be doing throughout the semester, finding equations of tangent lines. You know, so we were back in pre-calculus or in intermediate algebra, we were finding the average rate of change to find the slope between 2 points on a curve. You know, if this is, again, going back to the same problem, 1, 2. So back in pre-calculus, we got the equation of the line passing through the point where x equals 1, for example, and x equals to 3. All right, find the slope, and then use one of the points and the slope, and then from there, get the equation of the line. This time, now that we have the slope of the instantaneous slope, or the slope exactly at 1, well, so number 1, let's get to the equation of the line. We're using the point slope form. That is y minus y1 equals m times x minus x1. Well, that is, we need one point and we need the slope. The point, we can get the point from the function because we have the value of x equals to 1. This means the order pair 1, comma, we only need to figure out the y value. How do we get the y value? Plugging in x equals to 1 on the original function, right? F of 1, that's 1 squared plus 2, which equals to 3. So we got the point, and slope from the previous page what did we get for the slope for this? M equals to 2. So we're ready to get the slope. Y minus 3 equals 2 times x minus 1, and let's just solve for y in this case. So y minus 3 equals to x minus 2, that's y equals to 2x. Add 3 to both sides to get y equals 2x plus 1. Alright, so let's plot the two together just to check the consistency of the calculations and all that. So that's 1, 2, so 0, 0, 0, okay, that's 1, 3. And it's gonna go like this. And the equation y equals 2x plus 1, so we're gonna go 1 unit up, and then from here we're gonna rise 2 units and run 1 unit. So that's the equation. Rise 2, run 1. Isn't it a tangent line? So I think all we did here is consistent with the picture, the graph, the calculations. But again, guys, I know if you got a little scared about all the process that we did in the previous pages, okay, just know that we are not gonna do this forever. So this is just putting what we know from intermediate algebra, from pre-calculus, how to put it together to get to a new idea. Of course, we're gonna do this later in a more practical way. If you have any questions, I'll be around for a few more minutes.